Hi everyone. Thank you for coming. My name is Akshay, and I'm here to talk about Rust, Python, and data science. So a little bit about me. I've been a data scientist at Capital One Canada for about 7 years, and I come at this from a background in math and stats. So for anyone looking for a super technical CS-driven analysis of Rust and Python, I'm sorry, that's not me. At Capital One, we build tools for data scientists. We try to codify the knowledge that's been used to build models over the years into libraries, ranging from developer enablement all the way through predictive modeling. We're not just consumers of the open source ecosystem. We try to contribute as much as we can, whether that's PRs to H2O or HyperOpt, or releasing some of our packages. So I've listed 4 projects here: LocoPy, DataCompy, EdgeTest, and LazyScribe, and that's just from my team. Capital One is a very large organization, and we have plenty of open source projects like Data Profiler, Rubicon. We try to be good citizens of the open source community as well. Like many companies, our language of choice for data science is Python. When I first joined, I was told you can use any language, any tool you want to solve the problem. I was using R at the time because that's what I learned in university. But if you want your code to have the best chance at living a long life and being reused, Python is the way to go. It's just ubiquitous amongst our data science community. And that really shapes how we've built our tools. We now take a very strong approach of trying to create extensions to existing open source software, whether that's new feature selection methods as estimators in scikit-learn, or extending visualizations on Plotly. But there is one thing that we haven't tackled, and that's kind of performant code. We've taken the approach of, can we just be fast enough and feature-rich? We're taking almost R&D work from the modeling teams, hardening it, testing it, trying to distribute it in a well-tested manner. But as long as it's fast enough, we've sort of set the bar there. But it's had some unintended consequences. Sometimes like a data validation job, a data scientist will run it overnight and say, that's because I know when I get into work the next day, it'll be done. I'll look at that data size and say, this should not take more than half an hour. Something's wrong here. But they won't tell us because it meets their needs and they can move fast enough. But last year, we started to ask ourselves this question of, are we doing the most that we can, or can we be doing more? In the cycle of building a model, maybe we've taken away a couple weeks of dev time, but all of those experiments, all of the things that people try in the course of building a new model, that's all runtime that we could potentially cut down, and maybe we can iterate a little bit faster. So at the same time that we were kind of asking ourselves these questions, I went to PyCon last year. Did anyone here go to PyCon last year? Yeah, so there were a bunch of different talks about Rust and Python, whether it's improvements to Pydantic or Robin, the web framework. And it really, it was the right message at the right time. So the maintainer of Pydantic says, Pydantic v2, which is written in Rust, is between 4 and 50x faster. You can, if you just look up Rust Python benchmarks, you can find a whole bunch of blog posts like this one by Ohad Ravid saying we gained 100x runtime improvement without changing the API. And there are other advantages of Rust as well. If Microsoft estimates that 70% of vulnerabilities are related to memory safety, and Rust is memory safe. I'm sure many people here have had the experience of getting high vulnerabilities on their production pipelines and needing to scramble to fix those. So if we can tackle even a fraction of those, we have far fewer headaches to deal with. In particular, we're interested in this crate, Pyo3, which allows us to write code in Rust and expose it via bindings and Python classes and functions. And doing so, it really enables this tantalizing opportunity of drop-in replacements. I keep thinking about the idea that I could go away for a few weeks, rewrite the backend in Rust, drop a new version that has no user-facing changes, and speed up everyone's workflow by 100x, 150x. That sounds really exciting, but it's a little daunting as well. But before we go further, let's talk about why Rust is not the future of data science. I can get a little carried away going down technical rabbit holes, as any of my colleagues will tell you. The learning curve is steep. Coming from, like I said, a math and stats background, I learned everything I know about Python on the job. And it took me a while to write Rust. I thought I was being pretty buttoned up with the typing in my Python code. Absolutely not. The Rust compiler showed me very, very quickly that I had many, many gaps in my code. The borrow checker, I'll be honest, I still don't quite understand. I don't quite understand it. Lifetime parameters, don't ask me. There's lots I still don't understand, and I'm probably one of the only members of our data team who's had a chance to sink their teeth into this. As data scientists, model fitting tasks are, what we make our money with, and the ecosystem doesn't quite have the support that we need. Python is still the default language for most new methodologies, or packages like LightGBM, XGBoost are standbys. Although there are some people who want to change that. I reference it here at the bottom for those with eagle eyes. There's someone in the XGBoost discussion forum who says they want to rewrite all of XGBoost without a single line of C and all in Rust. That was in February 2020. I have not heard anything since, but I'll continue to check that link. And finally, a scripting language like Python, most of my colleagues work in notebooks. That's not the case with ahead-of-time compilation, so learn to love the compiler. I think I've perfected the amount of time it takes for me to go and get a coffee, speak to a friend, and come back just for something to be compiled. So it's a very different experience than most of our data scientists are used to. So to answer this question of when should we use Rust, or if we should use Rust, I did a few different experiments. The first one is let's go all the way. Let's do everything we can and see what is the impact that we can get if we took this idea to the extreme. So this is an example package, so an internal package similar to Great Expectations, where we define and validate data constraints. The idea is that you can describe your standard constraints from your training data, and then run your new data as you're scoring your model through those constraints. So maybe you want to make sure there's no mythical new state that appears in your address data, or that your FICO scores are within range. The basic structure is that we're looping through the configuration, then we're looping through every single check and running it against those columns. So it's a nested for loop. This is a perfect example of a package that is, quote, fast enough for our users. But there's a lot of room for improvement. And when I show some of the benchmarks for when I rewrote this package, I won't be talking about this kind of 100x, 200x improvement, because I don't think that necessarily frames execution time in a way that's productive. So at PyData LA in 2019, the HDB scan maintainers introduced me to this idea of step changes in productivity, that code that runs in 45 minutes is the same as 35 minutes. You're not changing your workflow, it's not changing your experience. So this idea that if we really want to make change in the way people work, we need to be jumping these levels. So we want to stay in this idea of interactive code, where you're not even tabbing out of your notebook as much as possible. So using a NumPy-based data structure, so a dictionary with the keys being columns and the values being NumPy arrays, we're able to write a Rust prototype using the NumPy crate that is significantly more performant than our stock package. So it's probably hard to see, but this line is our stock. Okay, the Rust stuff's going to look pretty good. So if you can't see the legend, just assume the Rust stuff is the faster one. This is our stock package, and this is the Rust prototype using, again, a NumPy-based data structure. The NumPy crate, I don't know if any maintainers are here or anything. Awesome for doing this work. This was really as easy as it could be for someone who can't write Rust. Also, one thing to know about these benchmarks, as I'll get into with like distribution, this is all run on my local machine. And benchmarks are really hard to get right, so take everything with a grain of salt. But thinking about this idea of changing in levels of productivity, at 5 million rows with 100 features, we're right around that barrier of interactivity, and we're at about 7 minutes execution time with our stock package. So immediately we know Rust is helping a ton. But this NumPy-based data structure is like not that practical for a lot of people when they get to larger data sizes. So what about like pandas? Unfortunately, I didn't see any like pandas equivalent to the NumPy crate in Rust. So I decided to do something that I wanted to explore, which is polars. So for those of you who don't know, polars is a Python library written primarily in Rust. It's a data frame library that promises some pretty weighty like improvements. 50x speed up versus pandas, multi-threaded performance, a streaming engine so you can do out-of-core computation. Of course, this is a huge shift for the majority of data scientists who are used to pandas, NumPy. This will take a lot of convincing, right, to move your first instinct from orienting around pandas to your first instinct to orient around a new data frame library. So in our second prototype, what I did is we have our Python stock package with pandas, and then we have our Rust prototype that leverages polars. And the results are even more outstanding, I guess, surprising. At 5 million rows, it's faster than our NumPy-based data structure. It's way faster than our stock package. And it really got us thinking there might be something here. The problem is that we have a lot, like, I unit tested this. This is all like working code, but it's a very limited version of our package. Some of the like customizations and extensions that data scientists expect to be available, it would take me weeks or months to code that same functionality into this prototype. So we already know, like, this is not something we can ship. And we've kind of changed two variables here, right? We're writing the loops and everything in Rust, and we're using polars. So we need to like isolate what is Rust doing, what is polars doing, and like where is that line? And where can we get the most benefit? So the second experiment is replacing individual components. Like, what if we just be a little bit more selective about what we're rewriting? Maybe rewriting like things that are more expensive and leaving the things that are less expensive. So in this example, what we'll do is write new scikit-learn transformers for data preprocessing in Rust with two variants, right? We're going to do a Rust polars variant, we're going to do a Python polars variant, and then we have our stock pandas. And the idea here is that we can hopefully isolate the effect of writing stuff in Rust from writing stuff in polars. We'll have two different cleaners. One is for data imputation, and one is for categorical encoding. So what we notice right away is that since we're not rewriting the main like scikit-learn pipeline loop, our vectorized calculations don't seem to gain that much from going to Rust. Like Python polars gives us a huge amount of benefit. So here we have our stock package, and then this line here is our Rust prototype, and then Python polars is actually outperforming it, but it's all within this kind of interactive zone. So I don't want to draw too many conclusions from the rank ordering there. But we see that we actually just gain a lot from going to polars. We don't need to write Rust necessarily. This is just estimating parameters for categorical encoding. So this is kind of a single column. But what if we do it for a more realistic use case where someone's going to do a whole data preprocessing pipeline, right? 100 features. In this case, it'll be 15 categorical, 85 numeric. They all have something, data imputation or categorical encoding. So by simply adopting polars, pipeline parameter estimation, so like fit on your scikit-learn pipeline, is like much, much more performant than our stock package with pandas. So we are seeing a massive benefit just from going to polars and not really thinking about Rust. But we do know in the back of our mind, like when we're writing these like loops and like longer running code, that Rust can be transformational. So the final experiment we did was, this was actually a challenge from one of my colleagues. He basically just said, what about Numba, right? At least internally, our experience has been that Numba produces the most performant code, but it's kind of, again, shifting paradigms. So again, we're going to compare Numba to like my novice Rust code. So if anyone here, like if any Rustaceans are here, I'm sorry if I'm misrepresenting the language, but this is what I could do with my limited experience. So if you look at the same, make a similar like query about speeding up Python, but you reference Numba, you'll see like 95x speed improvements, 150x speed improvements. Like there's clearly leverage to be had by going to Numba. So our question was like Numba, polars, Rust, like how do we navigate this space? So we'll take two Numba accelerated functions we already had and benchmark them against Rust polars. So the recursive function we're going to write in Rust, and the vectorized calculation we'll just use polars. The reason I did this is because an early prototype of the recursive calculation in Python polars was not even close. It was not on the planet. It was not worth. It honestly just messed up the axes. So, and for those of you wondering, where polars extends its API through a plugin architecture that allows you to write specific expressions in Rust. So that's what we're going to do. We're going to write a recursive calculation as a Python or as a Rust extension of the polars API, and then we're going to have our vectorized calculation in Python polars, and then finally our Numba like kind of control example. The good news is, for me, having put in the effort in coding this, is that our recursive calculation in Rust outperforms Numba by a significant margin, or at least not statistically significant. Please don't come after me. Personally significant margin. And that's really interesting to us because Numba feels like a departure for many data scientists from their normal data manipulation workflow. So if we're able to say, hey, you can stay in like a data frame API and still gain a lot, you just have to like, don't worry about the Rust under the hood that we're writing, then that seems really powerful. But it's useless if the vectorized calculations are nowhere close, right? If we're losing space, losing time on the vectorized calculations, I don't think we come out ahead. The good news is, on the vectorized front, which is all in Python, we track pretty well. You know, in this particular benchmark, we outperform Numba, but you know, it's within an acceptable range. You know, I'm sure if I ran this at a different time, the results would be closer, maybe farther apart, but we can accept this result. So it seems logically like adopting polars and writing a little bit of Rust for those really, really expensive calculations can be a really good solution for us, where we can get this transformational speed, but we don't have to worry about the risks of Rust. But this is the big question, right? Is it worth it? Linus's law says, you know, given enough eyeballs, all bugs are shallow. Every single line of Rust that I write or that one of my tooling colleagues writes is a line with very few eyeballs. If I were to go back to work tomorrow and try to deploy this, there's no one on my team that can help me debug it. And that's a huge risk. And every data scientist that relies on our code automatically becomes nervous because now if I go on vacation or if I go to attend another conference and something breaks, who's going to fix it? So there's a real challenge here in key person risk or bus factor, lottery factor, however you want to say it. And one thing has become very, very clear is that mass adoption of Rust is a non-starter. It's been very, very clearly communicated, you know, as I start to like showcase what it's capable of, that people are more fearful of the code going obsolete and being unmaintainable than they are excited about the future possibilities, which, as someone who's gone down this technical rabbit hole and has become very excited, is tough to hear, but it's very realistic, right? It's a realistic fear. It's a relatable fear. And the second part of this is, what will you do with all this time, right? If I ask my colleagues if they want me to make their code 200 times faster, they'll say yes. They'll say yes. If I tell them it'll take me 6 weeks and I won't be able to respond to their other bug requests, they start to falter. And then if I ask them what would they do with that extra time, like are they going to try something new, or are we going to do just the same thing but faster? Then it gets even dicier, right? Some people have a very, very clear understanding of these are the experiments I want to run, this is how I'd use that time, this is what I can't do because it's taking too long. And other people are less sure, right, about what they would do at that time. And as an organization, there's a big expense, and the keynote yesterday talked about it. There's a huge expense to working cross-language. So it's a tough question to answer, and not to be clickbaity about the title, but I don't know is the answer. To me, the most logical approach is to try and get people to move into the Polars ecosystem, start to write some of those extensions in Rust and ship it that way. Distribution and cross-compilation has become my nemesis over the last 3 weeks. So there's challenges ahead as well on that front. But that's where I net out. If anyone here has thoughts, I'd love to hear them. Please find me after. But yeah, that's my experience. Thank you.
Thanks so much for the talk. Do we have any questions in the room? I'll come over.
Hi, excellent talk. I wanted to ask, it sounds like you've gone on a meaningful journey learning Rust, and I hope to at some point. You're well ahead of me, but I'm wondering if there are insights or things you learned in the process of learning Rust that have helped you when working with Python and the PyData stack, and things that maybe, like, as you come down from the mountain, you can share with the rest of us.
The Rust book is amazing. Start there. That's the #1 thing. I learned so much from that. The practical exercises were awesome. And appreciate Python, really, truly. I can't tell you how many times I thought I was hit compile, go talk to a friend, come back, 7 errors. Oh my goodness. Floats and ints. Python handles them. It's great. Rust, you need to know. You need to know. So no, I think the Rust book is the biggest thing that I learned to leverage, and I found that it's really, really helpful. Pyo3, having those 2 pages open simultaneously was really helpful because not all features in Rust can be used when you're trying to create Python bindings. So knowing which chapters to skip also helped me a lot.
Any other questions? Oh, yeah.
Thanks for the talk. I'm curious what your thoughts on about switching away, from, maybe not switching your team to Rust, but maybe something a little closer, like Julia, to the same ecosystem and whatnot. And then also, what about just switching to like accelerators, GPUs, and you're talking about Polars or maybe like Rapids or cuDF, things like that. So just kind of other vectors you might go to speed up your users' codes.
Yeah, so the one other thing that we spent some time exploring was like Python. Unfortunately, as we started to go down that route, leadership was like, you spent 6 weeks on Rust. Maybe we should do some stuff that like people are going to use right now instead of spending another like 6 weeks on Python stuff. So I think that it's a very real concern about how much time we're spending on these R&D projects, because the internal version of this talk is here's a demo on something we may never use. So maybe I could have branded it a bit better. So we haven't looked at Julia or other like ahead of time compilation or other languages that we can leverage. And then in terms of like infrastructure things, our team's philosophy, generally speaking, is to be as platform agnostic as possible. We've seen a lot of change over the years of what infrastructure is available to us, how available GPUs are for our workflow. So we try to be as flexible and portable as possible. So that's kind of the first thing we think of. We've had the experience before where we wrote kind of GPU-specific code, and then the user said, I can't get a GPU provisioned. And that's an experience we really want to avoid. So that's kind of where we net out on some of that stuff.
More questions?
This is great talk. Thank you so much for doing this. I'm curious, it sounds like you had never worked with a compiled language before you started in Rust. Is that the case? So this was like your first time using a compiler?
Yes.
All right, like so much kudos. And you, in 6 weeks that you got this far, I think is actually very impressive. So thank you.
Thank you very much.
Anyone else? It's a big room.
Hi, I really enjoyed your talk. Let's take a look at the perspective of someone like a mentee or a student or something. Do you think that it would have been, from your perspective, valuable if they started with Rust and then went to Python, or the other way around, or maybe some third party other than that? Like, how do you think the restrictions and the sort of strictness of Rust relates to the learning experience?
So for most of my colleagues, coding is just like a means to an end, right? So they're using Python to answer like business questions or modeling questions. So I think that for them, the quickest way to answer that question is the most important. So I think that Python's flexibility, its interactive nature, its like low barrier to entry is the best way forward. I think there's a relatively small number of people who, at least in the data science world, who will benefit from going down to that lower level. And for those, I think starting with Python and going lower levels is probably the most efficient in terms of its likelihood of being relevant and its impact.
We have time for maybe one last question if someone has their hands up.
There's one over there.
All right. Very far again.
Hi, great talk. So what things or features you found in the Rust community that you would like to see in the Python community?
What a question. Honestly, as much as the compiler did annoy me, it was so helpful in telling me like there's so many like suggestions that the compiler provides to like make your code run. I think that some Python tools like the PyLance and extension of VS Code like get close to there, but as much as the compiler was annoying, and I think there's been plenty of like blog posts and stuff about the Rust compiler, it was really helpful. There were some times where I was like learning and writing, and then there's some times where I was like, I'm just going to hit compile, and the compiler will tell me what's wrong, and then I'll just go and figure it out. So I don't really know exactly how that would port to Python, but that's the thing I can think of right now. That helped me so much.
Thanks so much, Akshay. Please
Thank
give
you.
him a round of applause.